Hello and welcome once again to the Maths Jedi channel. This is another video in my A-level series. This one following up from some of the previous videos on algebraic fractions. Today's video is going to be on partial fractions. This video particularly focuses on one type of partial fractions. I'll do another video shortly on focusing on another type of partial fractions, so there'll be two parts to this particular chapter, but I'll do them separately so you can watch them on the playlist. If you're new to the channel, I really would appreciate if you could leave a like. That will help out the channel a ton going forward, just to help support our work, and would really help us a ton. So without further delay, let's talk about what partial fractions are, and let's just take apart how we do questions involving these things. Now, in previous videos, you'll be aware we've been talking about algebraic fractions. What we've been trying to do is add up two algebraic fractions to produce something that has just one numerator and one denominator. In some cases, we've left the denominator unsimplified as two linear factors, much like this. And what our partial fractions is the process of reversing that. So taking a situation when you've got a numerator and a denominator, and let's say the denominator is unsimplified like this, and then going back to the original question, so a way of reversing the order and understanding how that order could be reversed. It's very helpful to be able to do that so we can take apart very complex problems and understand them for later on. So partial fractions just talks about how we might go about doing that. There are two different situations we need to focus on at A level. One situation is where you have linear factors that are distinct, like this one. And the other situation is when you have linear factors which are repeated, which I'll do in another video later on. So this process is called representing a particular fraction in partial fractions, understanding how we separate out one numerator into two different numerators over two different distinct linear factors. We're going to look at an example. We're not going to look at this particular example, but we are going to look at another one. We're going to look at this example, 7x minus 1 over x plus 1, x minus 3. Now I'm going to refer to this previous example just a little bit, just to have a bit of cross-referencing so you can understand what's going on. In this example here, we have x minus 5 and x plus 3 in the denominator. And if you look back at the original question, we also have x minus 5 and x plus 3 in the original denominators. So it's important to emphasise that I know already what my denominator is going to look like. One of them is going to be x plus 1 and one of them is going to be x minus 3. The two values on the top, we don't yet know what's going on with these. One's we're going to call A, one we're going to call B. We don't know what these values are, we have to find them. But in separating out the fraction, the combined fraction, into two partial fractions, we establish these two constants. We look for ways in which we can understand how these two constants work. So here is what we're trying to create, a situation where the original numerator and the two denominators are becoming two partial fractions, one with a constant above the denominator of x plus 1 and one with a constant above the denominator of x minus 3. You can see this is stronger than an equation, it's actually an identity. We're saying these two things are absolutely identical regardless of the value of x. If we were looking just at the right hand side, what we try and do is multiply up. So we'd have a lots of x minus 3, hopefully you understand we're multiplying by x minus 3 here, and b lots of x plus 1, and then of course the denominator being x plus 1, x minus 3. Because the bottoms are the same, the denominator is the same, we look just at the top bits. We can say let's take the top parts, the numerator parts, and look just at those. We'd have a situation where 7x minus 1 is equal to a brackets x minus 3 plus b brackets x plus 1. We're going to call that equation 1. There are two ways of progressing from here. We can either use a suitable substitution by using values of x to work out what's going on, or we can equate coefficients. Either way works very effectively. To be honest, I personally prefer to use substitutions. It just seems to be a bit more logical to me, and I understand it a bit better. But of course, equating coefficients is also equally valuable. In using substitutions, it makes sense to try and use a substitution where you're going to get rid of one of the values. So you can see already on the screen that I just showed you, we're making x be minus 1. And we let x be minus 1 because if we did, this bracket becomes 0, and therefore b becomes irrelevant. You can see them doing that here, and that gives us a nice easy substitution which can work out very quickly what the value of a was. A is 2. If we go back a step, it would make sense now to use the value x equals 3, so we can do the same thing, but this time eliminate the value of a. And this gives us the value b equals 5. This then gives us the answer, 2 over x plus 1 plus 5 over x minus 3. It's very easy to do it. In terms of equating coefficients, if I go back a step, it's important to multiply out this bracket here and this bracket here. So we would have ax plus bx if you look at the x values. So we know that a plus b must be 7. We also know that minus 3a plus 1b must be minus 1. So you can set up a simultaneous equation system to work out what the values of a and b are in a similar way to what you did at GCSE. As I said, I much prefer using substitution because it's a really simple method and it just suits my logical brain. So we're going to look at another example now. For this particular example, we're going to use equating coefficients to show you how it works. So again, similar to before, we're just going to write it out as two partial fractions, 1 over the denominator of 3x minus 2, 1 over the denominator of 2x minus 1. We're going to show that by multiplying out through 2x minus 1 and 3x minus 2, we'd end up with the numerators 2x and a lots of 2x minus 1, so this times this, and then b lots of 3x minus 2, this times this. So that's a numerator expression. And then in this example, let's just create coefficients. So you can see we would go through with 2ax minus a, and then plus 3bx minus 2b. So similar to what I just described. And again, if you gather together the expressions that are x expressions, you'd have 2a plus 3b, and then minus a minus 2b. Now in this example, this part is the number part, and that will be equal to 0, and then 2a plus 3b is equal to 2. So you can use that to set up a simultaneous equation system, and they do that really quickly here. And that's what they're doing. And they're using simultaneous equation solving to work out the values of a and b. So this is how you would do it using equating coefficients. If you're going to use substitution, just going back a step, you'd probably use a suitable value for x. So in this case, it would be 2/3. If you put x equals to 2/3 in, that would make this bracket 0 and so on. And this one here would be a half. So if you put a half in, you'd get 0 in this bracket. So those two values of x would be able to be used as substitution values to give you the a and b values in a similar way to before. Either way, you always get to the answer with 4 over 3x minus 2 and minus 2 over 2x minus 1. Take care with negative coefficients that you can see they've placed a minus in the middle there to equate those two partial fractions in that way. This works very similar if you have 3 distinct linear factors, and you should be expected to solve questions that have 3 distinct linear factors at A level. Very, very similar, just this time we use 3 coefficients, A, B and C. In a similar way to before, we'd have to work out what would happen if we were adding all these things up. So as with before, we'd be multiplying through by x plus 1 and 2x plus 1 on A. B would multiply by x minus 3 and 2x plus 1. And C would multiply by x minus 3, x plus 1. So those things taken into account are very important for the next part. Here again, we can use substitution to get rid of values if you want to. For example, if I let x be 3, that would get rid of b and c straight away because these brackets become 0. This bracket would still be alive. If I let x be minus a half, that would get rid of a and b and leave me with c. If I let x be minus 1, that would get rid of a and c and it would leave me with b. So there are ways of using substitution to get these values out. That's exactly what they're going to do here. So they're substituting x equals to 3. That gets you the a value very quickly. A is 1. And then we can use that a as 1 in future texts, of course, it's now that we know it. So they're going to use b, substitution x minus 1. They're going to get a value very quickly, minus 2. Why do they use minus 1? You can see minus 1 plus 1 is 0 here, minus 1 plus 1 is 0 here, so that gets rid of a and c straight away. So to find c, we can either use substitution x equals minus a half. Why is it minus a half? Because you can see that minus a half here would give you a 0 bracket, minus a half here would give you a 0 bracket, it would leave you with c. So that's the way you could use substitution to find c. They do another way on the next page, so you can see them working their way through a situation here where they were equating coefficients. Again, this can be quite complicated, but they get to an answer eventually, which they make c equals 2. To be honest, I'm much more comfortable with using substitution to work my way through it. Still gives us the partial fraction answer, 1 over x minus 3, because we knew that a is 1. B was minus 2, so you can see them using minus 2 here. And then c finally is positive 2, so you can see them working their way through here. As I said, I would much prefer to use substitution, but you can go about it with equating coefficients. What they've done here is looked at multiplying out the brackets and understanding the number parts plus 1, and then they've equated coefficients appropriately to get the value. We will look at repeated factors in the next video, but for now, let's just head off into the book and look at some questions. So bear with me a minute while I set that up. Welcome back. This is now exercise 1D. This is on page 11 in the A2 book. So of course, this is where you should head now to do some practice on those methods. We're going to look at a couple of these questions just to give yourself a little bit more confidence, and hopefully you can then work your way through the remainder of this exercise in your own time. So I'm going to start off by looking at question 2, and I'll also do number 5 just to give you a good experience of both. But as I say, you can work your way through the others here to make sure you've really got yourself a good understanding about what's happening. It's important to mention when you haven't got linear factors, like in part E here and part G here, you would use the hint here, factorising appropriately to get your linear factors. So always use factorising here to make sure you get back to your linear factors before you start partialising, because of course you need your linear factors. Note the difference of two squares there. So the linear factors here would be x minus 3, x plus 3, and so on and so forth for each of these. Just make sure you factorise first. We're not going to look at these, but we are going to look at number 2 and 5. So I'll start off with number 2. You'll see straight away that we've got two linear factors, 4 plus x and 2 minus x. They're even telling you in the question they want it set out in that way. So let's just write this out. We have to find the numerical constants a and b. So now we're going to imagine what would happen if I was multiplying out the bottoms to get the common denominator 4 plus x, 2 minus x. Of course, a would be multiplied by 2 minus x, and b would be multiplied by 4 plus x, and that would be equal to minus 2x minus 5. Then we're going to use substitution, so it'd be sensible to use a value of x here that makes this bracket 0. So I'm going to use the value x equals minus 4. So if I do that, I've got minus 2 lots of minus 4, so that's positive 8. 8 minus 5 is 3. And then 2 minus minus 4 is 6. So that's 6a. And this bracket obviously will be 0, so obviously this will disappear. And that gives me the value of a as a half. On the other side here, let's make a suitable value of x to get rid of this bracket. So x should be 2 here. 2 minus 2 is 0. So we're going to get minus 2 lots of 2 is minus 4. Minus 4 minus 5 is minus 9. This bracket's gone, so this is gone. And then 4 plus 2 is 6, 6b. So minus 9 over 6, of course, we try and simplify it, divide it by 3. So minus 3 over 2 is b. That then, we have to express that as a partialised answer. So I'm just going to rub out to the top here, and we're just going to represent that accordingly. So using these values, we've got half a, so of course we'd have 1 on the top, and we could write 2 on the bottom here. That's perfectly fine, or you could write half on the top, it's up to you. And then this one here would be minus 3 on the top, 3, and then 2 lots of 2 minus x on the bottom, because 3 over 2. So that's the way you would write it, partialised. You could also put the constants, the half and the minus 3 over 2 on the top if you wished. Let's trash my notations. Look at number 5, it's similar to the one I showed you in the PowerPoint. They're giving you the expressions to aim at. Let's just squash it in. 3 factors here, of course, x, 2x plus 1, and 3x minus 2. So we're going to have 3 factors on my values. They're not using a, b, and c, just noticed. So let's try and stay with what they're using, d, e, and f. And again, what we're going to do is think about what would happen if we were multiplying out all of this stuff to collate the fractions together. So for d, I've been multiplying d by 2x plus 1 and 3x minus 2. So 2x plus 1 and 3x minus 2. For e, I've been multiplying by x and 3x minus 2. And for f, I've been multiplying by x and 2x plus 1. Sorry about going over the other page, but just squeeze in for now. Equating the numerators together would then involve us doing just this. Now let's look at values of x that we could use strategically. Well, first of all, if I lose x is 0, will get rid of e and f and leave me with d. So let's do that straight away. This gives me on the left hand side 0 here, and then 2. And that gives me 0 plus 1 is 1, and then 0 minus 2 is minus 2, so it's minus 2d. So d is minus 1. To leave me with e and get rid of d and f, I need to make x be minus a half. You can see that working here and here. So here we've got some complicated work to do, but we can do it. So minus a half squared is a quarter, so it's minus 10 over 4. And then 8 times minus a half is minus 4, so it's going to be plus 4, because 2 negatives make a plus, and then plus the 2. And over here on the right hand side, we've got this one's gone and this one's gone, but it leaves us with minus a half, and then minus 3 over 2 minus 2. E. It is complicated with fractions, that's why sometimes people do prefer to use equating coefficients. It's completely up to you, to be honest. With the modern calculators that you have, of course, it's much easier to go through this process now because you've got modern calculators as well to help you. So you can actually use the calculator to do a lot of the donkey work for you. You don't have to keep your brain working through these fractions. So I'm going to put up the calculator here. We'll just work our way through this particular one just to get ourselves a good understanding. So I'll do the left hand side first. So minus 10 over 4. Plus 4 plus 2. You'll often find the values are quite nice as well. So it's 7 over 2. And then this bit here, we'll do the brackets first. So minus 3 over 2 minus 2. And then we're going to multiply that by half, minus a half, minus a half. 7 over 4. And then of course we've got to do 7 over 2 divided by 7 over 4. I'm lazy, so I'm going to use the calculator, but you could work it out. So 7 over 2 divided by the answer, of course. Let's get that looking right. Answer 2, very easy. So 2 is E. To work out f, you could use substitution. You could let x be 2/3 here to get the values, or you could use equating coefficients. Because I've got d and e already, I'm actually going to just put in a very simple value of x. So I'm going to let x be 1 here, just because I want to create a very easy sum for myself rather than working with complicated fractions. For this last one, I'm going to cut corners a little bit. So I've got on the left hand side minus 10, minus 8 here, so that's minus 18, plus 2, that's minus 16. So minus 10, minus 8, and then plus 2. And on the right hand side, I've got 2 lots of 1 is 2, plus 1 is 3, and then that's going to be 3. So this is going to be 3 lots of 1 is 3, minus 2 is 1. So that's going to be 1, 3, so 3D. And if I put 1 here, I'm going to have 3 minus 2 is 1 again, so that's just E. And if I put 1 here, I'm going to have 2 lots of 1 is 1, 2 lots of 1 is 2, sorry, plus 1 is 3, 3 lots of 1 is 3, so I have 3f. So you can see, by using a simple number, I've managed to get down to a fairly simple expression quite quickly, and because I know what d and e are, I can put those corresponding values in. So I know what d is, because that's minus 3, and I know what e is here. Oops. E is 2. there's 3 lots of 1, 3 lots of minus 1, sorry. And then that's 3f. So that gives us minus 16, then we get add the 3, so that's minus 13. Take away the 2, it's minus 15. So minus 15 is 3f. And then finally we divide by 3, so I know that f is minus 5. So you can see that helps cut corners a little bit for that last one, just avoids working with some complex fractions. You can see that's where it becomes a little bit easier. You can use some of the algebra just to help you a little bit, make it a little bit more simple to do. So D, E and F are minus 1, 2 and minus 5. You do need to make sure that you've written it out properly. So before I will stop, I will just show you that this is not the answer just yet. You will have to express it with these values in place. So D was minus 1, so let's just put minus 1 up there. E was 2, and then F was minus 5. So lastly, I'm just going to make sure that's shown. So this would be the last line of your work. This would be the last line of your problem to show that you've written it out partialised, otherwise you won't get the full marks. The examiner wants to see you, for completeness reasons, to making sure that's stated so that you actually have understood that you've partialised this into 3 distinct fractions. Okay, those are the only examples I'm going to do. So 2 and 5, the only 2 I did. Both of them exam type questions. You can see how many marks they're worth. I would now encourage you to go back through and work your way through the remainder of this exercise in your own time. That's it for today's lesson. So thank you very much for watching, and I'll be back shortly to talk about working out partial fractions with repeated linear factors. Thanks very much for watching. Bye bye for now.